All right, here we go. Reaction video number 22. Today I did a search for, I think, honors physics homework or something, and I found an entire playlist that has a whole bunch of circuits. And since yesterday we were doing the very beginning scaffolding stuff with a different teacher, I thought I'd jump ahead to one that was called complex circuits, which, just looking at the circuit, looks like we're probably going to be doing some equivalent resistance and trying to, current and voltage. Okay, so let's hit it.
So let's go ahead and work through some of these homework problems here. So I'm going to start, and for these first four problems, we're doing the exact same thing, finding the total resistance, finding the total current or voltage, and then the voltage and current on each resistor.
So that was really cool how he was scaffolding. He said, look, my goodness, we have four problems. We all have to do the same thing. And so they're all going to be different. But this approach, this recipe, this scaffold is always going to help you. So yesterday I posted a link to a blog post of mine where I really get frustrated with how much work the equivalent resistance approach is. And so, I talked about my spreadsheet approach. But I think that, as long as you sort of stick with it and understand what you're doing, of course it works, right? And this first example, this is not going to be that hard. Let's see, I'm going to 4, 10, 10 amps, you know what I mean? You can sort of do it quick in your head for nice round numbers like this. And by the way, using round numbers is super, super great because if you want students to check things like, wait a minute, is all the power provided by the battery equal to the power dissipated by the resistors? If you use nice integers that work out well, and sometimes you might have to futz with it if you're building your own problems, you can avoid some of the sort of round-off errors that can really throw students off. Now, on the other hand, the student who thinks critically about that says, oh, you know what, I bet you if I rounded this differently, it would have worked out. And that is a good skill to know. But in these early stages when we're scaffolding this stuff, I think nice round numbers is smart. The only big problem that I see with using round numbers, and I run into this all the time, is that in the lab, you're probably not going to be running into 5 ohm, 20 ohm, and 6 ohm resistors for two reasons, or frankly, for that matter, 100-volt batteries, for a couple of reasons. So the internal resistance of batteries is, on this order, in this vicinity, and you don't want the internal resistance to change your calculation very much. And the other reason is they're going to have a ton of current through them, and so they're going to burn up. So, typically if you put a K in front of every single one of these, that would be much more realistic. That's what's going to happen in the lab. But then you're going to have milli in front of all of your currents. And so it kind of depends, like with these early problems, which way is the best way to go.
So I'm going to start, of course, by looking for simple combinations, and I see that right here. I have R2 and R3. So I can say 1 over RT equals 1 over 20 plus 1 over 5 because they're connected in parallel.
Cool.
I go ahead and I combine those and I get that my total...
A quick pet peeve. I love how he wrote this. This is the way that I like to write the equivalent resistance for parallel. Very, very often what people do is they will write this as R1... R1 times R2 divided by R1 plus R2, right? Which is what happens when there's 2 and you kind of combine it into a single fraction and flip it over. So then the question is, what is the extension for the third one? Well, it's not R1 times R2 times R3 divided by R1 plus R2 plus R3. I mean, that doesn't even another 8 units, right? So that doesn't extend, but this structure absolutely extends. You can keep on trucking. Duck, 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 duck. And of course, the reason is that the derivation of this just comes from a straight application of sort of Ohm's law and thinking about what's happening in the current, with the current in the circuit.
Resistance here, the combination of 2 and 3, is going to be equal to 4 ohms.
Yep.
And then I can go ahead and redraw my circuit, replacing that resistor with a 4 ohm resistor. So I still have R1 here, which is 6 ohms. And then I have R23, which is 4 ohms, connected to this 100-volt battery. I then find the...
So a couple of things. So a gut check for me, I guess this was 4 because my gut check for parallel is always smaller than the smallest one. Well, my smallest one was 5. Figured it was a little bit less than 5, so I went 4. So I don't know if you heard me whispering before, but I said 4 and then 10 because I added the 6 to make 10, which is what's about to happen. And then, quick 10 amps. The other thing is I love the fact that for these simple problems, it really doesn't matter which way you hook the battery up, right? So It determines the direction of the current, but it doesn't really affect things like power. Well, I guess they're not calculating power; they're just calculating voltage and current. Let's watch to see if he sticks with this, because current through doesn't bother me, but voltage through is problematic. I would normally say voltage across, but these are subtle things, and so really we're just trying to get the students to churn this stuff out so that we can attack more interesting problems later. All right, let's keep going.
Total resistance of that combination. They're connected in series, R1 in that combo of 2 and 3, so I'm just going to add them up, and I get that the total resistance of this circuit is 10 ohms, which answers question A. From there, I can go ahead and find...
Just one more. You hear me saying this all the time, these video solutions compared to written. So, I mean, that he wrote a 0, but come on, it looks like a 6, right? And his 6s look like that. Where else has he written a 6? Imagine if all a student had was this printout. 16, how the heck you get 16? But he said 10 as soon as he wrote it, and I believe he repeated himself. He said, oh, so the answer is 10 ohms. So it's really a great way to be, it's a forgiving medium, right? Because you have two different presentations. You have what's written and what you say.
And the total current, which is the current leaving the battery, and I'm going to do that by doing Ohm's law, V equals IR. So I can say 100 volts equals the current times my 10 ohm resistor, and I end up finding that my overall current running through this circuit is going to be 10 amps when I solve for that.
And another example of the beauty of the SI unit system, right? If you've got voltage, volts, and you've got resistance in ohms, trust me, your answer is going to be in amps. Technically, this answer, I suppose you could say, is volts per ohm, right? But that's a fancy way of saying amps. So yeah, that was really cool. So I'm just gonna. I think he hasn't quite done it yet. He hasn't done this voltage. Oh, he still needs to break it down. So in my blog post, what I was talking about is we're only halfway through the problem now. So a lot of students get here and they're like, oh, sweet, I found the equivalent resistance. But we're only halfway done because we have to go back. We sort of have to undo this. He's really done 2 steps here. He did 1 step here and 1 step here. You have to undo both of those steps to go back and figure out the current through everybody. Now, the first one's relatively straightforward, but then you got to figure out the split. So equivalent resistances, you go all the way down, you make your equivalent circuits. You're basically saying, hey, this battery is working just as hard if you were to build this in the lab as it is with this in the lab. So since that's true, this one's easier to analyze, so whatever current we find here must be true up here. But then you have to sort of go back and say, oh crap, now this current has to split. So I find that equivalent resistance problems are tricky because I have found that students are pretty good at getting exactly where he's at now. And then they're not as great, or they get crabby having to build it back again. So I'm really curious to see how he does that.
I then can go back and apply the voltage and current for each one. So that 10 amps that leaves the battery is going to go through both of those resistors there as it travels around the circuit. So this resistor will get 10 amps. This resistor will also get 10 amps. Then using Ohm's law, I can solve for the voltage across each one. And so we're going to keep coming back to that one, but most of these are designed to be relatively quick math you can probably do in your head.
Nice.
So we're going to say our voltage is current 10 times resistance, which is 6. So this one gets 60 volts. This one gets 40 volts using that same equation there. Okay, I can then step this back to my previous example here. This R23 came from combining 2 and 3 in parallel. I know that resistors that are combined in parallel each get the full voltage, so I can say that R2 is going to get 40 volts, and
Love that.
R3 is also going to get 40 volts.
Yeah, that's super cool.
I can then use V equals IR once again to get the current. So 40 equals 20 times I, R2 is going to get 2 amps. 40 equals 5 times I, R3 is going to get 8 amps. And so those are my answers for that. And then for R1, that one didn't change, so that one's going to be 10 amps and 60 volts.
So really great work, really great work. A couple of things that I noticed that a great way to easily check your numbers, right? So because these are nice, beautiful round numbers, you can say, oh, 60 plus 40, oh, that equals 100. What do you know? And 2 plus 8 equals 10. And when I think about what students struggle with is they say, oh my gosh, I don't understand where these extra volts came from, because 60 plus 40 is already 100, and then I'm adding another 40, that gets up to 140. How does that work? So the huge difference between the way that the voltage works and the current works in these circuits is super, super tricky. But I think that it's really great the way that he set up, just slowly break it down and then build it back again. And he built it back again really fast, right? And because this is a relatively straightforward problem, I'm just going to skip ahead. I'm not going to necessarily turn the sound back on. Looks like.
All right, moving on to my next circuit here.
Yeah, so let's take a look if this next circuit is going to get us in trouble. So this circuit, right, it's going to be tricky, right, because these two are going to be probably 3, and then that's 10, 20, and then we've got 5 amps coming through, right? So, I mean, because this one is down here as opposed to up here, students might not realize they can immediately combine these to be 17. So there's just so many interesting things, and I'm just going to go back. There we go. I think I'll stop here, but these problems are the sort of foundation of how to analyze circuits like crazy. And I really liked how he started with one that I guess, it was about as simple as you could do, right? Because they've already done just a parallel. They've probably already done just a series. So this is the best example of the very next one to do. So really cool job. All right, thanks everybody. I hope you have a great day. And remember, physics teachers are awesome.